Curvilinear coordinate systems 11. A second toroidal system using coordinates xi, eta, and phi can be formed with these coordinates related to the Cartesian coordinates by this set of equations. And we already talked about part C, which is obtain the scale factors for this toroidal system. Now we're going to talk about part D, express the position and displacement vectors in this system. Okay, so first of all, how can I write the position vector in this new coordinate system? The position vector R is going to have a component on the unit vector xi hat, and that's going to be in xi hat direction, plus we will have a component on e eta hat, it's in e eta hat direction, and then we will have a component on e phi hat, and that's going to be in e phi hat direction. This is the position vector we have to find. So this is the question in part D. Now, first of all, I have to remember how to write these unit vectors. So xi hat unit vector is going to be 1 over the scale factor h psi del r del psi. So I've already calculated the scale factors and this derivatives in part C. So I'm just going to look for those results and copy them here and then divide it by the scale factor. So first of all, what was the scale factor h psi that we have found in part C? Let's recall it. It is A divided by cosine hyperbolic eta minus cosine psi. So 1 over the scale factor will be this divided by A. Now what is del r del psi? So that's what we have found here. Minus A sine psi sine hyperbolic eta cosine phi ex hat over cosine hyperbolic eta minus cosine psi parentheses square. So let's copy this for the x component here. So this is equal to this is the x component, and then we had the y component, which is here. So we can plug that in. This is the y component. And then we had the z component, which is here. So we can copy this as well. So this is our z component. And this will be multiplied by 1 over h psi, which is cosine hyperbolic eta minus cosine psi divided by A. All right, so this will give us the unit vector xi hat. So we can now see that xi hat is equal to, in the ex hat term, we have one cancellation of one of these terms and a's will cancel. So we will be left with minus sine psi sine hyperbolic eta cosine phi divided by cosine hyperbolic eta minus cosine psi in ex hat direction. And then we have for the y component here, a's will cancel and one of these terms will cancel as well. So we will get minus sine psi sine hyperbolic eta sine phi divided by cosine hyperbolic eta minus cosine psi in EY hat direction. And for the z part, we have again a cancellation of a's and one of these terms. So we will have plus cosine psi cosine hyperbolic eta and minus 1 divided by cosine hyperbolic eta minus cosine psi in EZ hat direction. So we have found E psi hat. All right. And remember that the position vector R was given also here. So we can just copy this position vector. Here is our position vector again. So I need to take the dot product R dot E psi hat. So R dot E psi hat will give me, you can see the x components will be multiplied. So I have a sine psi here. So minus a sine psi. I have the squares of these terms. Sine hyperbolic eta squared cosine squared phi divided by cosine hyperbolic eta minus cosine psi squared. That's this first term from the x components. And then I will have the y components. So here's a minus sign, here's a plus sign, so it's going to be minus minus a. Again, I have a sine psi, sine hyperbolic eta squared, sine squared phi divided by cosine hyperbolic eta minus cosine psi squared. And then I have the z part, which is a sine psi cosine psi cosine hyperbolic eta minus 1 divided by cosine hyperbolic eta minus cosine psi parentheses squared. Now you can see that here I have a cosine square phi and a sine square phi in this term. So it's the same thing multiplied by cosine square and sine square. So I'm going to have a simplification. So this will give me minus a sine psi sine hyperbolic eta squared And then I will have the z term a sine psi cosine psi cosine hyperbolic eta minus 1 divided by cosine hyperbolic eta minus cosine psi squared, because cosine square phi plus sine square phi is equal to 1. Okay? And this I can write in a sine psi parentheses, a sine psi cosine psi cosine hyperbolic eta and then I have a minus 1 and so minus 1 from this term and a minus sine square sine hyperbolic eta squared divided by cosine hyperbolic eta minus cosine psi parenthesis squared. All right. Now I have to remember what is 1 plus sine hyperbolic squared. So this is what we have done here. You can see 1 plus sine hyperbolic x squared is cosine hyperbolic squared. So that's what I'm going to substitute here for minus parentheses 1 plus sine hyperbolic eta squared. So this will give me a sine psi cosine psi cosine hyperbolic eta, and here I have minus cosine hyperbolic eta squared divided by cosine hyperbolic eta minus cosine psi parentheses squared. All right. So if I take this into a minus parentheses, I will have minus a sine psi, and then I take it into a cosine hyperbolic eta parentheses. This will become cosine hyperbolic eta minus cosine psi. So one of these terms will cancel. So I'm going to have this divided by cosine hyperbolic eta minus cosine psi in my final answer for this term. Now similarly, we're going to work on E eta hat. This is equal to 1 over the scale factor h sub eta multiplied with del r del eta, and now we have to copy the result for del r del eta. So let's go back to that calculation. So for the x part, this was our final results. So let's copy that. We're going to have a cosine phi 1 minus cosine hyperbolic cosine divided by cosine hyperbolic minus cosine squared. This is in Ex hat direction. And then we have the y component. Let's see, what was the y component? Y component is here. All right. Let me also resize this. This is our y component. And then we had the z component, del z del eta, which is here. Let's copy that. This is our z component in ez hat direction. And this whole thing will be divided by 1 over divided by h eta, which was equal to h psi, so cosine hyperbolic eta minus cosine psi divided by a. So the same thing, the same factor here. Now we're ready to write e eta hat. Okay, so for the first term we have a cancellation of a's and one of these terms will disappear. So we're going to get cosine phi 1 minus cosine hyperbolic eta cosine psi divided by cosine hyperbolic eta minus cosine psi in ex hat direction, plus for the second term, again, a cancellation of a's and one of these terms. This will give us sine phi 1 minus cosine hyperbolic eta cosine psi divided by cosine hyperbolic eta minus cosine psi. This is in EY hat direction. And for the last term, we have minus, this cancels and one of these cancel, sine psi, sine hyperbolic eta, this is going to be in EZ hat direction, divided by cosine hyperbolic eta minus cosine psi. Okay, and let's recopy the position vector r so that we can take the dot product with it from the previous part C. This is our position vector. And now we can look at r dot e eta hat. So for the x components, we have a sine hyperbolic eta, a cosine square. So we're going to get a cosine square phi multiplied by this. And then we will have, for the y component, sine square phi, a sine hyperbolic eta multiplied by this. So we can write both of these terms with this parenthesis. So let's do that. We're going to get a sine hyperbolic eta cosine square phi. And then we will have a sine hyperbolic eta sine square phi. And this will be multiplied with 1 minus cosine hyperbolic eta cosine psi. And for the z part, we will have minus a sine square psi sine hyperbolic eta, and this is divided by cosine hyperbolic eta minus cosine psi squared. And this can be taken into a sine hyperbolic eta parentheses as well. So we will have in that parenthesis cosine square plus sine square, which is 1. And then we have 1 minus cosine hyperbolic eta cosine psi. And in the last term, we also have a sine hyperbolic eta. Therefore, we have a minus sine square psi. Now, as for 1 minus sine square psi, we can substitute cosine square. So this can be written as, and obviously this is also divided by cosine hyperbolic eta minus cosine psi squared, and that will give us a minus a sine hyperbolic, it's not squared, in this term, so in r dot e eta hat, it's going to get squared, yes. Minus a sine hyperbolic eta cosine 1 minus sine square. 1 minus sine square becomes cosine square. Cosine square psi minus cosine hyperbolic eta cosine psi. I can write this in cosine psi parentheses, and you can see that if I do that, I will have cosine hyperbolic eta minus cosine psi as one of the terms. So this is going to give me a cancellation of one of the cosine hyperbolic eta minus cosine psi's. All right, so that's what I'm going to obtain for r dot e eta hat. So once again, here I obtain cosine square psi, cosine psi parentheses. This gives me cosine psi minus cosine hyperbolic eta. And you can also think of this as cosine psi minus cosine hyperbolic eta parentheses squared. So that cancels out with that. Introducing a minus sign here, I have the original form, cosine hyperbolic eta minus cosine psi. Okay. And finally, for E phi hat, I have 1 over the scale factor h phi del r del phi and this time let's take a look at what was del r del phi. Looking at our r vector here, this is actually particularly simple. You will get a minus sine phi, a cosine phi here, and no contribution from this side. So I can just rewrite this. With that observation, I have a minus a sine hyperbolic eta sine phi, cosine turned into minus sine, divided by cosine hyperbolic eta minus cosine psi in EX hat direction. Then I have plus a sine hyperbolic eta sine turned into a cosine, cosine phi divided by cosine hyperbolic eta minus cosine psi, and this is multiplied by 1 over h phi. What was h phi we calculated? It is a sine hyperbolic eta divided by cosine hyperbolic eta minus cosine psi. So it is, the reciprocal will be cosine hyperbolic eta minus cosine psi divided by a sine hyperbolic eta. And what does that give us? So you see the bottoms will disappear and sine hyperbolic etas will disappear. We will get a simple result, minus sine phi EX hat plus cosine phi EY hat. And let's recall our position vector from part C again. This was our position vector. Here is our position vector again. So we can calculate r dot e phi hat, and that is equal to minus a sine hyperbolic eta cosine phi sine phi for the x parts, and for the y parts I will get plus a sine hyperbolic eta sine phi cosine phi. You can see that these two are divided by this term basically, but these two are adding up to 0. So I can write my position vector, which was the question. R dot e psi hat was calculated here. Minus a sine psi cosine hyperbolic eta divided by cosine hyperbolic eta minus cosine psi. This is in e psi hat direction. And then for the component on e eta hat, we had this answer. So let's copy that. We have, this is an e eta hat direction and no contribution from the phi part. Therefore, this is our answer for the unit vector written in the toroidal coordinate system. Now, what is the differential displacement vector, dr? It is del r del psi d psi plus del r del eta d eta plus del r del phi d phi. This is basically the scale factor h psi d psi e psi hat plus h eta d eta e eta hat plus h phi d phi in e phi hat direction. So we can write this differential displacement dr What is the scale factor h psi? Let's recall h psi and h eta were the same. They were both equal to a sine hyperbolic eta divided by cosine hyperbolic eta minus cosine psi. So if I go back to h psi, it was, no, for h psi it was a over cosine hyperbolic eta minus cosine psi. So let's recall that. A over cosine hyperbolic eta minus cosine psi d psi in e psi hat direction. And for h eta was the same. The same term here. So I have plus a over cosine hyperbolic eta minus cosine psi d eta in e eta hat direction. And for the phi, the scale factor was this, a sine hyperbolic eta divided by cosine hyperbolic minus cosine psi. So plus a sine hyperbolic eta divided by cosine hyperbolic eta minus cosine psi d phi in e phi hat direction. So this is the final answer for the differential displacement vector. Okay, so in order to write the position vector in the new coordinate system using the new unit vectors, first of all we have to find what the new unit vectors are, which is calculated by taking a derivative of the position vector with respect to that unit vector and multiplying it by 1 over h psi, because h psi is the magnitude of this, so therefore we obtain a unit vector pointing in this direction. So I have performed this calculation for psi, eta, and phi. So the unit, first I found the unit vectors written in terms of ex hat, ey hat, and ez hat. Then I take a dot product with the position vector written in terms of ex hat, ey hat, and ez hat using the coordinate transformations between toroidal and Cartesian coordinates. So taking the dot products with e psi hat, e eta hat, and e phi hat, I can find the prefactors for these unit vectors, which is what I have done here, and that gave me the result I was looking for. And for the differential position displacement vector, we take a derivative of the position vector with respect to each of the new coordinates and multiply it by a differential change in those coordinates and add them up. So this is basically del r del psi d psi, del r del eta d eta, and del r del phi d phi. So we add them up. And these are simply equal to the scale factors multiplied by the unit vectors. So if I already know what the scale factors are, I can just plug them in from part C, and this will give me the answer I'm looking for.